All right, share. We don't need to. I'm familiar with the basic ideas of probabilities. So 29. All right, our next step is the introduction of a probability function. This is a function that assigns to an arbitrary event associated with the sample space a real number between 0 and 1, inclusive. We start by discussing ways in which probabilities are assigned to simple events in the sample space S. Let's get our definition here going on. All right, so given a sample space S, remember these are events. All right, within simple events, to each simple event E sub I, all right, so I goes from 1 to n, we assign a real number denoted by P of E sub I. So this is the probability of that event happening. These numbers can be assigned in an arbitrary manner as long as the following two conditions are satisfied. The probability of a simple event is a number between 0 and 1, and the sum of those probabilities should be 1. That means it's 100% chance that one of these things is going to happen. All right. So like if you have like, a coin flip, right? Event 1 is heads, event 2 is tails, right? Event 1 would be 0.5, event 2 would be 0.5. So you add 0.5 and 0.5, you get 100%. It's 100% chance that it's going to be either heads or tails, right? All right, so there's your basic breakdown, okay? So any probability that satisfies these two conditions is an acceptable probability assignment. And then we're going to talk about heads and tails. So does not explain how acceptable probabilities are assigned to simple events. These assignments are generally based on the expected or actual percentage of times that a simple event occurs when an experiment is repeated a large number of times. So we might assume that a coin is fair, meaning it's perfectly 50% heads, 50% tails, but how can you know for sure? Right? You could like try to build it where it's perfectly flat, right? And perfectly balanced somehow, right? Using physics and technology. But still, how do you know? Well, you could flip the coin like 10 billion times and be like, well, half, 5 billion up, 5 billion down, but you still don't know. You only know that out of 10 billion times it was 50-50, right? This is a philosophical argument, isn't it? But it's still a legit argument, right? Probability is about the unknown. There's no way you can actually know for sure, right? When we assign these probabilities to, heads up or heads down, that's a deep philosophical argument. There's different kinds of approaches philosophically to probability itself, which has big ramifications in say like quantum mechanics, which says that the entire universe is probabilistic. And so let S, so we want to say the assignments are reasonable. Well, talk to Aristotle, I guess. Let a experiment be the flipping of a single coin. Let us choose a sample space. So it's either heads or tails. If it appears to be fair, we are inclined to assign probabilities as 0.5 and 0.5, or 1/2 and 1/2. They're based on reasoning that since there are two ways a coin can land, in the long run, a head will turn up half the time, and a tail will turn up half of the time. These probability assignments are acceptable since both conditions for acceptable probability assignments stated in the preceding box are satisfied, right? These add up to 1, and each one is less than 1, right? Pretty loose requirements, right? the probability and statistics didn't always exist. Only a couple, 300 years old, right? And of course, it was discovered by mathematician gambling. Okay? So if we were to flip a coin 1,000 times, we'd expect a head to turn up approximately, but not exactly, 500 times. The random number feature on a graphing calculator can be used to simulate 1,000 flips of a coin. So figure 3 shows that with their simulator, they got 497 heads the first time, 495 heads the second, and 504 heads the third. So no matter how many times you do this, you're never going to get exactly 500 and 500, right? That would make it real confident to say, oh, it's 50-50, right? But how do we really come up with 50-50? Every single time you do the experiment, you very rarely get actually 500 and 500. You just do this experiment over and over and over and over and over and again, and then look at the average, right? The average would be 500. Okay. So if, however, we only get 360 or 376 heads in 1,000 flip coin, we might suspect the coin is not fair. Then we might assign the simple events in the sample space based on if we only did one experiment and we got 376 heads and we assigned our probability that way. All right, that's also an acceptable assignment. But the probability assignment, 1 and 0, is acceptable. It's not reasonable. You could say, well, hell, let's just say heads is 100% of the time and tails is 0% of the time. All right, it's acceptable because 0 and 1 add up to 1, and 0 and 1 are both between 0 and 1, right? But that's not reasonable. This one, we say, okay, let's give 60% to heads and 80% to tails. It's not acceptable because they don't add up to 100%. Okay. So keep in mind that out of the infinitely many possible acceptable probability assignments to simple events in a sample space, we're generally inclined to choose one assignment over another based on reasoning or experimental results. Okay. Given an acceptable probability assignment for simple events in a sample space, how do we define the probability of an arbitrary event associated with S? All right, so given an acceptable probability assignment for the simple events in a sample space, we define the probability of arbitrary event E, called P of E, the probability of that event happening, as follows. If E is the empty set, then the probability is 0. All right, so the probability of nothing is nothing. Okay? If E is a simple event, then the probability has already been assigned, right? Because that's what we did. Like for the heads and the tails, we're assigning the probability of each event. All right, so when you have a sample space for each, they call it a simple event. That means an event that only has one thing in it, one thing that can happen. All right. If it's a compound event, then you add up the probabilities of all the simple events. Okay. So a compound event could be, what's the probability of heads or tails? How can I write this? I'll just write or. Right? Well, that's the probability of heads plus the probability of tails, right? Or 0.5 plus 0.5, which is 100% chance that you're going to get heads or tails. Okay. So this would be, I think they just put a comma here. How do they do it? Probability of heads or tails. Well, the whole sample space was heads and tails, right? So you just add them up. If if E is the sample space S, so this is a special case. That's the one I just showed you. Okay. We need one with more events in it for me to get more into the compound stuff. So we want to think about things like what's the probability of throwing heads on a second flip if you've already flipped heads on the first? Well, it's 50-50, right? Because what happens on the second flip has nothing to do with what happened on the first flip, right? But what's the probability of getting two heads in a row, right? That's a different question. So let's turn to example 2, the tossing of a nickel and a dime. So you can get a heads, 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 tails, tails, heads, and these are different because the first one is the nickel and the second one is the dime. Okay, so the heads on the nickel is different than getting the heads on the dime. There's 4 simple outcomes, and the coins are assumed to be fair. It would appear that each outcome would occur 25% of the time. So here we set up our probability sample space. We give each one, we assign each one 25%, right? This is an acceptable assignment because they add up to 1, and each one of those numbers is between 0 and 1. It's reasonable, all right, because we're assuming they're perfectly balanced coins, all right? What's the probability of getting one head and one tail? Okay, well, you'd have to take the probability of this plus the probability of that, right? So this A would be the probability of getting tails heads for heads tails, the probability of tails heads plus probability of heads tails should be 1/4 plus 1/4 should be 1/2 or 0.5 or 50% chance, right? Because it's 2 out of the 4 possibilities. What is the probability of getting at least one head? Okay, so it'd be any of those 3. The probability of heads, 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 tails, tails, heads. The probability of heads, heads, plus the probability of heads, tails, plus the probability of tails, heads, or 1/4 plus 1/4 plus 1/4, or 75%, right? And what is the probability of getting at least one head or at least one tail? Okay, that has at least one head. This one has at least one tail. So this is going to be 100%, right? We'd have to add them all up. 1/4 plus 1/4 plus 1/4 would be 1. What's the probability of getting 3 heads? That's not in the sample space, right? They told us the probability of the empty set is 0. So probability of the empty set, right, is 0 because there is no 3 heads. Simple stuff, right? We have to build up these basics though and get the notation down. Really, we're building notation here because as soon as this starts to even get just barely a little bit complicated where your brain just goes, well, that's a simple question, but I don't know. We need to have this notation that we're going to build in these simple cases and that we're going to use this notation as mechanics, right? Because eventually we're going to be multiplying probabilities, dividing probabilities, doing all kinds of stuff with these, okay? I should have started with this chapter, you know? Well, it's an algebra class. I guess they could have done the algebra and then got into this. So here they give you a procedure. Set up an appropriate sample space, assign the acceptable probabilities. To obtain the probability of an arbitrary event, add the probabilities of the simple events in E. We're not going to do a match problem because that's boring. A minute. There we go. Okay, example 4 illustrate 2 important ways in which acceptable and reasonable probability assignments are made for simple events in sample space. Each approach has its advantage in certain situations. A theoretical approach, we use assumptions and a deductive reasoning process to assign probabilities to simple events. No experiments are actually conducted. That's what we did in example 4. I skipped match problem 4. Um, so the coin toss thing is like completely theoretical, right? We can imagine in our minds, say, perfectly fair coins and produce the perfect statistics, right? In the real world, there's no such thing as a perfectly fair coin. Empirical approach, we could assign probabilities to simple events based on the results of actual experiments. So we skipped match problem 4, but it's the same. But the thing is when we assign our probabilities, instead of just assuming these theoretical coins that are perfectly fair and balanced, instead we take a real world coin and we test it. We flip that sucker over and over and over and over and over and over and over again and look at how many times it's flipped heads and flipped tails, and then we would assign our actual real world probability, right? Empirical probability concepts are stated more precisely. If we conduct an experiment n times and event E occurs with frequency f of E, then the ratio of f of E over n is called the relative frequency. All right, so this is the number of times that events happened out of n tries. So if you flip the coin 500 times, that's n is 500, and then you got 250 heads, right? F of n over E, that's the relative frequency. That's where we get the 1/2 from, okay? We define the empirical probability denoted by P of E by the number, if it exists, that the relative frequency approaches as n gets larger and larger. So you just keep flipping the coin, flipping the coin, flipping the coin, flipping the coin. So we're taking the limit as n goes to infinity of f of E over n. Y'all don't have limits yet. But there is no such thing as flipping the coin an infinite number of times. But the more times you flip it, the more confident that you are that it's a fair coin or that it's not a fair coin. Okay. So for any particular n, the relative frequency is also called the approximate empirical probability of that event. So for this section, we're going to use the theoretical approach. In the next section, we'll return to the empirical approach. We're not going to make it to the empirical approach. So here we're doing everything purely theoretical in our brain. Equally likely assumption. In tossing a nickel a dime, we assign the same probability, 1/4, to each simple event. Right? There's 4 things that could happen. We just assume that these are perfectly fair coins, right? And assigning the same probability to each event in S, we're making the assumption that each simple event is likely to occur as any other. This is the equally likely assumption. Okay. So in a sample space with n elements, we assume that each simple event is as likely to occur as any other. We assign the probability of 1 over n to each. So there's 4 possibilities. You have 1 over 4 as the probability for each event. All right, so under an equally likely assumption, we can develop a very useful formula for finding probabilities of arbitrary events associated with a sample space. If a single die is rolled, and we assume that each face is likely to come up as any other, then for this sample space, the probability of rolling a 1 is going to be 1 over 6, because n here is 6, right? That's the probability of rolling a 2, or probability of rolling a 3, probability of rolling whatever, right? It's all 1 over 6, 1 over n. More theorem. So if we want to think about rolling a prime number, 2, 3, and 5 are prime, right? So like we said before, you just take probability of that event, a prime number, the probability of each of the simple events that make up that event added together. So it'd be 1/2, because this is 3 out of the 6 things that you could roll, right? So far, this is a whole lot of words for really simple concepts, right? We're throwing in some math. And this notation is what allows us to extend these simple concepts into the realm of the complex. So we assume that each simple event is likely to occur as any other, then the probability of an arbitrary event is given by the probability of that event, the number of elements in the event. So in that last one, there was 3 elements in the event, divided by the number of elements in the whole sample space. So there's 3 out of that event, 6 possibilities in the sample space because there's 6 sides on the die, right? Or 3 out of 6, which we can write as this, n of E over n of S. Let's look at another simple example. Consider rolling 2 dice. Assume that each simple event in the sample space is likely to occur as any other. Find the probabilities. All right, so E1 is a sum of 7 turns up, right? So what is E1? Let's see, we could have what, a 1 and then a 6, right? We could have a 2 and a 5. We could have a 3 and a 4. So since we're rolling the 2 dice at the same time, right? A 4 and a 3 is the same as a 3 and a 4, right? We're not saying one's the first roll and one's the second roll. We're rolling them at the same time. So order here doesn't matter. And I think that's it. A 3 and a 4. Okay. What are all the possibilities though? What is our sample space? You could have a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4. Let's take it too long. Just copy and paste those. Right? So they don't bother writing out the sample space, but so to get a sum of 7, all right, there are 3 different possibilities, right? The results found in example. Okay, so they're using the, okay, that sucks. So basically, there's 36 possible things. You got 6 possibilities. So for the first die, there's 6 possibilities. The second die, there's 6 possibilities. So there's 36 total possibilities in your sample space, right? Here, we need to double these because we have to consider these. I was hoping we didn't, but we do have to consider a 1 and a 6. A 1 is on one die, 6 on the other, or you could get 6 on the other die and a 1 on the other, right? So if we're looking at a sample space of 36, we have to duplicate these. All right, so there's 6 possibilities out of the 36. All right, a 1 and a 6 or a 6 and a 1, because the dice are distinct from one another. If we want a sum of 11, well, you can either get a 5 and a 6 or a 6 and a 5. All right, so there's only 2 possibilities out of the 36. So our probability is 1 out of 18. If the sum is less than 4, 1 and 1, 2 and 1, and 1 and 2. Okay, notice this 1 and 1, we don't put it twice. Like these are different because there's 2 different dice. All right, this one you get a 1 and a 1. Okay, so there's 3 possibilities out of the 36. There's only one way to get a 12, and that's a 6 on each of them. So it'd be a 1 out of 36 chance. So far, this is still pretty easy stuff. Just a whole lot of words and vocabulary, right? But the concepts aren't bad. Y'all could figure this out without any of this vocabulary so far. Okay. Simulation and empirical probabilities. Use output from the random number. We're not going to do this. I'm using random numbers. All right, I guess we could look at it here though. We'll look at their solution. We're going to use a random number feature. There's no such thing as a true random number on a computer. something that's impossible to happen. Computers are unable to be completely random unless you use a quantum computer. All right, determine the empirical probabilities of the following events and compare with the theoretical probabilities. So they are rolling 100 rolls of 2 dice. So to get a sum of 7, what's the probability? Or a sum of 11. So a graphing calculator can be used to select a random integer from 1 to 6. Each of the 6 integers in the given range is equally likely to be selected. Therefore, by selecting a random integer from 1 to 6 and adding it to a second random integer from 1 to 6, we simulate rolling 2 dice and recording the sum. I mean, this isn't all that helpful. This is just calculator nonsense. The empirical probability is 15 out of 100. So there's 100 rolls, right? There's only 15 of them that can that can add up to a 7. Okay, so it'd be a 15%. So that's using our empirical abilities, right? Purely thought, right? Not the, oh, hold on. Yeah, so this is where you're actually doing not theoretical but empirical, where you're actually doing the experiment. Although I don't think it's not a real experiment, it's on a computer, so it's still theoretical in my mind. But in their like emphasis, they're saying this is like an experiment. Okay. Of course, it comes out to the same as what you would get using the theoretical probabilities. No, they emphasize it's not. So on the calculator, they're getting 0.6. The theoretical is 0.056. So out of 36 possibilities, what is this? To get an 11, right? We saw up here, to get an 11, right? It's 1 out of 18 or 2 out of 36. A decimal is 0.056. They're showing that if you use a calculator and do the same experiment, you don't get exactly that, right? This is a probability. This is the legit theoretical probability, right? But in the real world, if you actually rolled the dice over and over again, so they're rolling the dice 100 times. So we're looking at this, looking at the 2 dice, seeing how many add up to, how many rolls of the dice add up to 11, all right? So when we do the experiment, we don't get the theoretical probability, right? If you flip your coins over and over again, you don't get 50% in the real world. That's the probability of it, all right? So if you use your calculator to mimic rolling dice, you don't get exactly the same as the theoretical, but you do get something fairly close, unless it's a really bad day, right? You ever played Monopoly and rolled like a 2, like 42 times? Yeah. I don't want to do a match problem. Look at example 7 here, so if we can use some of this. All right, drawing 5 cards from a 52 card deck without replacement. What's the probability of getting 5 spades? That's a good question, right? Simple question, kind of hard to answer, right? Unless we think about it. So the sample space is all 5 card hands from a 52 card deck. All right, the last class was pretty easy. Like, how many different ways can you have 4 diamonds in your hand, right? It didn't refer to the whole deck, right? It was just like you're only looking at the diamonds and putting them in your hand. Here we're actually drawing cards from the 52 card deck. So now the numbers get big. All right, so how many different 5 card hands can we have total? All right. The order in the hand doesn't matter. So the number of 52 card hands is 52, choose 5, right? Which would be 52 factorial over 5 factorial times 52 minus 5 factorial. That's the number of possible hands, all right, which apparently is 1,287 different hands you can have. So our event E is the set of all 5 card hands from 13 spades. Again, the order does not matter. So this would be 13, there's 13 spades, we're choosing 5. So that'd be 13 factorial over 5 factorial times 13 minus 5 factorial. So that's how many 5 card hands have 5 spades, okay? So our probability, we take the probability, basically the probability of our event, or the number of possible hands we could get out of the total possible hands available. So, sorry, there's 2,500,000 possible hands. There's 1,287 hands you can get that would have 5 spades, okay? So we get a probability of 0.0005. All right, some calculators will display it as 4.95. So they've rounded it, basically. The calculators rounded it to 0.05% chance. All right, so y'all have the basic mechanics now. Y'all got the jargon. Let's see, we could look at another one. Let's look at this last one here. All right, the Board of Regents of the university is made up of 12 men, 16 women. If a committee of 6 is chosen at random, what is the probability that it will contain 3 men and 3 women? All right, this would be easy if there's the same number of men and women, right? So first we have to set up our sample space, right? What are the possible 6-person committees we can have? There's 28 people total, right? 16 and 12. So we have 28 people total and we're choosing 6. So that's our total number of possible committees that we could have, okay? Now we need to figure out how many fit our criteria, and then we simply divide. And from what we learned in the last section, we can figure out how many fit our criteria. So we need a 6-person committee, 3 men, 3 women. All right, so we need to find the number of events in this event space. All right, so first off, we're going to select 3 men. There's 12 of them available. It doesn't matter what order. One's not president, one's not vice president. So it's simply 12 men, choose 3. Then the second operation is we're going to select 3 women out of the 16 available. So that's 16, choose 3. So remember the multiplication principle. We have to take these numbers and multiply them together. All right, which is a pretty big number anyhow. You multiply those together, and that's the total number of committees that have 3 men and 3 women out of all the possible assumptions, right? So our probability is the number of events that fit our criteria divided by the total number of events, right? Total possible number of committees you could have, and you divide, and you get a reasonable number, 0.327, right? If you get like 15, you did something wrong, right? When you're doing probabilities, this number had better be between 0 and 1, otherwise you screwed something up, all right? Okay. That's it for 8-1. Let's end it there. 8-2, 8-3, and 8-4 will be extra credit in my math lab. Okay. But I recommend you work on it. It's important stuff. It's one of the most important things you could probably learn in college is the next 3 sections of this class. That's what I said. It's because it's a college algebra class, not a college statistics class. Right? But yeah, that would have been more important than some of the things I think we've covered. Yeah. Yeah. All right, let's get out of here. Yeah. Y'all have good luck on your finals.